Hey guys, welcome back to Bump Up Chem. In this video, we're going to be looking at molecular orbital theory, which doesn't take too much of a large place in the IB specification, but we're going to go through the very basics and how to apply some very rudimentary skills. Firstly though, have a go at this question. Draw the electron in a box diagram to show the hybridization of the s and p orbitals in an sp2 hybridized carbon. Pause the video and have a go. Okay, so thinking about this refreshed question, if we draw out the electron configuration that we would expect for carbon just using a regular electron in a box diagram, we end up with 2 electrons in the 1s, 2 in the 2s, and 2 in the 2p. Now when we've got an sp2 hybridized carbon, of course, we're going to combine the 2s orbital with 2 of the 2p orbitals, but obviously leave 1 of the 2p orbitals unhybridized, giving us 4 electrons spread equally across those orbitals. So what is molecular orbital theory anyway, and how does it compare to what we've already looked at? So in valence bond theory, we kind of look at a theory where the electrons are localized between 2 atoms, i.e. bonds, and the overlap of the atomic or hybrid orbitals is what generates sigma or pi bonds. Now, this is really useful for predicting the shapes of molecules, but it does have other limitations. So what does molecular orbital theory offer us? Well, it recognizes that electrons are delocalized throughout the molecule and that these individual atomic orbitals combine to form molecular orbitals. Now, these orbitals are no different than atomic orbitals. They have specific energy and they contain 2 electrons. However, they are spread over more than 1 atom. Now, it can help our understanding of molecular orbital theory to consider electrons as waves, and then we can start to conceptualize the interference of these wave forms as they overlap and interact with each other. So we can have 2 types of interactions of waves. So I'm going to represent these using a simple line. Of course, this is just a representation. It's not actually happening like this. But basically, we can have different types of interference. So if we think of constructive interference, if we have 2 waves and those waves are both in phase, then the peaks and the troughs of those waves line up with each other. However, we can also have destructive interference in which the phase is out and the peaks and the troughs of each wave exactly cancel each other out. This is called destructive interference. Now, when we draw the outcomes of these, with the in-phase waves, we would end up with an increasing amplitude of the waves at the peaks and troughs. But the out-of-phase graph we would see would be a massive reduction in the amplitude if it didn't completely remove all amplitude altogether. So we see a decrease in amplitude. We can use this wave interaction as a model for molecular orbital theory. If we think of constructive interference as something that's going to be a bonding force, it's going to increase the attractive force between atoms, and it's going to cause most of the electron density to be between atoms, and we'd call this bonding orbitals, which make up our sigma and pi bonds as we've already discussed. In the case of destructive interactions, this is a repulsive force. It's decreasing the attraction between the atoms, and we can visualize this as thinking about there being a node between the 2 atoms, and that node obviously is a place in which there is very little electron density. Obviously, electron density, the thing that allows the nuclei to be attracted to each other. So with the inclusion of these nodes, we weaken the bonds. And these are labeled as anti-bonding orbitals, which are exactly the same in the signs we use, sigma star and pi star, the star representing that these are the anti-bonding orbitals of the normal bonding orbitals. So this combination of atomic orbitals is called the linear combination of atomic orbitals, LCAO, and the number of orbitals is always going to be conserved, but the combination of any two orbitals will result in one bonding and one anti-bonding orbital, and they'll have a different shape than that of the initial atomic orbitals. For example, let's take one p orbital and combine it with another p orbital. So in this case, we're going to make one bonding and one anti-bonding orbital. So what does this look like? Well, in the case of the anti-bonding orbital, we're going to have very little electron density between the two atoms and electron density facing in the other direction altogether. And in the case of the bonding orbital, we're going to create a molecular orbital that has a lot of electron density between the nuclei. So that's the bonding orbital. And you can actually see in the anti-bonding orbital, that space between the nuclei is what we call the node. And that is the exact reason that electrons in those orbitals contribute to interatomic repulsion instead of attraction. So two p orbitals combine to make two molecular orbitals, one anti-bonding and one bonding. Electrons in the bonding contribute towards attraction, and electrons in the anti-bonding contribute towards repulsion. So how can we work out where these electrons are going, which ones are bonding and which ones are anti-bonding? Well, we can use molecular orbital diagrams. So here we're going to look at H2, really simple. So one atom of hydrogen has one electron and another atom of hydrogen has another electron, both in the 1s. So all we're going to do is we're going to take these two orbitals, and any two atomic orbitals would create one anti-bonding and one bonding orbital. So if we imagine bonding these together, we're going to create one high energy anti-bonding and one low energy bonding orbital. And then we're going to be able to add the electrons and determine the bonds that are at play here. So the bottom box represents sigma orbitals, so a regular bonding orbital, and the top box represents sigma star or anti-bonding orbitals. So remember, any electrons going in the bottom orbital contribute to bonding, in the top orbital they contribute to repulsion. So we've got two electrons in total to add, so we're just going to follow our regular electron filling rules, and both of the electrons go into the bottom sigma bonding orbital because we fill up the lowest energy first. And so we can see here in H2, the molecule, we're going to have two electrons in those bonding orbitals and no electrons in the anti-bonding orbitals. And you might think, well, what's this really for? Well, let's have a look at how we can use bond order to be able to predict whether we'll have single, double, or triple bonds. So we can use the diagram that we've just drawn to be able to determine whether we have a single, double, or triple bond present. This is called using bond order, and it has a very simple calculation that we can apply to our diagram. So the equation is quite simple. To work out the bond order, we just take the number of bonding electrons, we subtract the number of anti-bonding electrons, and we divide the value by 2 to give us our overall bond order value. So in this calculation, we have 2 bonding electrons, 0 anti-bonding electrons. 2 divided by 2 equals 1. So this would of course be a single bond for H2, which we may have already known in this case. But what is also interesting about the bond order is if we are to get fractional values or decimal values, then that tells us there is likely to be delocalization in the molecule. So we have another use for it there as well. So let's have a look at something slightly more complicated like O2, which is of course oxygen bonded to oxygen. So I'm only going to show the valence shell here, as we won't be looking at the inner electrons. And of course, we have 6 total valence electrons on each side. And then we're going to go about filling up the electrons in our molecular orbital section down the middle. We have, of course, sigma and then sigma antibonding. And then we have our p orbitals split into a sigma and then 2 pi bonding. And then we have a pi antibonding and a sigma antibonding up top. So filling the electrons in using Aufbau principle and Hund rule, we've got a total of 12 electrons. So we just start filling those electrons in from the bottom up. So we've got 4. Now we're going to fill in the p orbitals separately first because of the repulsion within the orbitals. However, in this case, that doesn't matter. For the first set of bonding p orbitals, we're going to fill up all 4, leaving us 2 electrons remaining, which we're going to put in each individual antibonding p orbital to finish up. So using the diagram we've made and the equation for bond order, we can then calculate the bond order. So the number of bonding electrons minus the number of antibonding electrons. So we have a total of 6 bonding electrons, or 8 if we include the 2s, but if we don't include that, it won't make a difference to our calculation. And we're going to subtract the antibonding, which is 2, or 4, again, if we want to include the 2s, divided by 2, which is going to be 2, therefore giving us a double bond for O2. So time for some practice questions, and really do pause the video and take a go at these. So firstly, draw the molecular orbital diagram for He2. Pause the video and have a go at that. Pop 'em up. So of course, each helium atom having 2 electrons, giving us 4 in total. That would give us a bond order of 0. And we would expect that because of course He is a noble gas, so won't actually form a bond with another helium atom anyway. Okay, next one, draw the molecular orbital diagram for O2, 2+. Pause the video to have a go at that. Pop them up. So here we're going to have only 3 electrons in these p orbitals, and that is because we've got a 2+ charge, so we've lost 2 electrons. So we've got 3 on each side. So let's add those in. We add in 2 to the sigma bonding and 4 more to the pi bonding orbitals, with none being added to the anti-bonding orbitals. Last question to finish us up for molecular orbital theory then. What is the bond order of O2+ that we just drew a diagram of? Pause the video to have a go at that. Pop them up. Well, of course, here we have 6 bonding electrons, no non-bonding electrons over 2, which is going to be 3. So we've got a bond order of 3, which will be the oxygens joined by a triple bond with a lone pair each and a 2- charge. And this makes sense because if we think of O2 normally, if we were to remove 2 electrons, the lone pairs from the oxygens would have to move down from one of the atoms to form the bonding pair that would then allow both oxygens to see a complete octet. So once again, no practical for this video, but some questions to do. Thanks again for joining me, guys. Don't forget to like, subscribe, hit the bell icon. Come on, you know the drill. Practice makes slightly better.